teaching. It's my pleasure to be present here to give this talk about our advancements in teaching AI in medium level education. So it's sort of turning the previous topic upside down. So this is not about using AI in education, but it's about educating how AI actually functions. That's what the entire research faculty I'm working for here is all about. Yes. Okay, so in our presentation in 2024, we already introduced our AI-enhanced robot setup, which is an industrial robot. So I'm sorry, no fancy humanoid robots. It really is about industrial machinery, which is supported by AI, which is then linked with some digital control lines to a physical digital interface, which is then linked by USB to an AI-optimized PC, essentially very expensive, very powerful electronics hardware, which also contains then a graphics card, which is meant for actually running the AI module. Always be prepared how you set up a PC like this. It also contains a very high-powered frame grabber card, which will capture image from an industrial camera, which is physically mounted onto the robot, which can also have a couple of digital control lines to actually activate the camera. So it's a sort of closed system, electronics-wise. It also contains a software package from a professional provider of machine vision tools already since many decades, with essentially a two-stage software. One, which is sort of C# interface-based software, which handles the AI model. And then a second package, which is sort of the AI trainer. It contains a graphical user interface where you can actually construct an AI. The other software then handles the data flow to and from this model. Compared to our back then setup, we also installed a few more goodies. For example, what we call the YOLO test stand. It's a sort of card front transportable system with webcams, Jetson Nano. That's an AI-enhanced microcomputer for about $80. So it's so we can scale it to multiple installations like this for our education purposes, where we run this open source image recognition software. We also installed yet another high-powered computer so we can run our own AI models. And this is a photograph of the entire setup. So I'm sorry, it's extremely technical and it's very hardcore for engineers, but that's what my faculty is. We are hardcore engineers and nerds. So that's what this is all about. So last time when we presented this, it was all about how we then use this setup to teach to our students how AI is actually structured and how it basically functions. One of the demystification process about using an AI is once the students have actually understood what's inside these models and how it actually works, they're sort of disappointed. They have some sort of magic ideas, but at the end of the course, I always tell them, look, an AI model is an oversized Excel tape. That's it. It's a terabyte of arrays of numbers, nothing more. Once they understand how it works, they sort of understand its limitation and its function. We intended to use this setup with robots and AI in a sort of two-lane increased complexity approach, from kids without any coding experience all the way to our high-trained bachelor students, from just programming a robot with some very simple functions, and I'll show you how simple it actually is, all the way to train AI models and interconnecting robots to AI models, because that's one of the major problems with most people don't see coming. If you use AI, you're sort of looking at the screen, you put ciphers in, ciphers are coming out, but with a robot, you have to get the information somehow to the AI, and then afterwards, you must program what the robot is supposed to do with information. So it's lots of programming all around this AI module, and that's what our teaching is mostly about. So our course then focus on actually training deep learning AIs for machine vision and how to program the robot to properly interact with that AI. So these two prongs were sort of our main focus of training exercise. So this also developed into a long lecture, and just to see how such a lecture looks like, it's about 3 introductory lectures about applications, theory, coding, and hardware, 2 lectures and 1 exercise with this open source model. Then, then another 2 lectures and 1 lecture exercise with the robot and this above mentioned industrial AI system. And then 1 lecture with the home assignment, how to use the PyTorch template to solve the MNIST problem. Now there comes a big question mark. What is the MNIST problem? Now, the standard exercise for every coding student who learns programming in any programming language is always this hello world program. Now, every code programming book starts with that. As boring as it is, but that's how they all start. For AI networks, the equivalent hello world exercise is to solve the data set of MNIST or the extended MNIST, which a gentleman named Jan LeCun has created as an introductory task for his AI teachings. That's something you find lots of information about, videos, online help, whatever. And one of the reasons why we chose this is to actually, to come to your point, Isabel, that we had to sort of encourage our students to use AI, because this is a topic which is rather complex. And the task is then to use, with the help of AI, the information and find the solution to the problem which I posed then. So the classical endless data set was not mentioned for using AI to solve it, but to recreate a neural network which can recognize this data collection of 70,000 images, which is sort of the handwriting of Mr. Jan LeCun's students. I wonder how he convinced them to do that, because it's freaking lot of work. To scan these handwritten symbols and sort of put them into a data format which the programming language Python can then actually read. In order to simplify this, and I'm a kid from the 80s, I sort of changed that, and I created a sort of simplified 8x8 pixels data set with the Commodore 64 character set, because then the data set becomes a lot smaller and much easier to handle if you don't have a high-powered computing system at your disposal. So this can run on any laptop exercise. Now, the 3 tasks which we then give our students inside our course, so just to sum them up, was A, use this YOLO, you only look once, open source AI module to recognize any chosen object. In that example, it was medical instrumentation, but we have whatever the students choose to, we simply tell them, yet bring along whatever and find a way how to use this properly. The second task was to then recognize the color and type of target and target these little colored steel balls from a very famous German manufacturer of kids' toys. And then program the robot such that he will move its camera into a certain position, recognize the arrangement of the balls, and then sort them. The silver ones here, the other ones there. Sounds simple, but that's what 99% of industrial robots do in factories. Pick and place, sort stuff, and that's what industrial robots is all about. If you can AI enhance this, there are millions of possible robots who would like to be enhanced. Now, that is, of course, by far more complicated and requires a lot of code interface, which has been provided by me, but still, it's a bit of a programming task. Then the top of the 9 task was to use this PyTorch framework. A framework is essentially a very large library of functions and ways to make creating an AI network much easier. PyTorch, for example, is the framework which enables Tesla cars autonomous driving. That's what this framework model is about. Then our students receive a template, which I sort of sabotage. I made it such that it actually provides extremely poor performance. And it gives them the C64 dataset. And I mean poor performance with the endless dataset. And then the task for the students is, with the help of some AI, to explain what the problem is, find where I place the sabotage, solve the problem, change the input structure of the set data of the network to accept the C64 dataset, because it's not obvious, and then achieve somehow above 95% inference recognition rate success. Now, that's, of course, a method which I sort of devised how to use AI in education, sabotage the entire system, because just asking then Gemini or whatever to create a code segment which solves this problem is a 10-second line, and then you have to code and that's it. But if you sabotage the software and try to explain that to an AI, that's not so obvious to make that actually work. And that's the core of the exercise. Now, if we then make some analysis how this course actually works, the reception was actually very positive. Our students were always enrolling to the maximum of possible seats in this course. Now, how good is then the didactic success in all of this? And when we compare here a couple of criteria from swiftness to industrial experience, it actually became quite fragmentized. It was not quite clear which part of this 3-pronged approach had the best impact. Now, YOLO is easy to use, but it's a ready-made package. There's not much you can do about it. The cheapness, of course, for free. I mean, it's a very powerful software. It is for free. Its capabilities are great, but industrial experience goes to 0. I mean, it's an open source model. It's not what industry is using. If you compare that to the industrial system, you also find it's excellent in use. It's very powerful. Experience is great. cheapness is poor. I mean, if you pay $10,000 or euros for one license, you're sort of broke. You can't do this with a course of 20 students in it. So the educational value is also mediocre because, of course, it's like Excel teaching. I mean, Complex Vision controls 50% of machine vision market worldwide. So it's really close call. Compare that to our experience with our PyTorch assignment. Now, Swift is a success. It's a bit of work to actually get this functional and to make students understand how this code is structured. So the education value is great. It's very cheap. Capabilities, of course, are extremely limited. So it's not quite clear. It's a confusing image. There's no clear win in all of this. So we have to focus on something. So we said we should focus on education and cheapness of implementation. I mean, we're not missed. We don't have that kind of funds available to buy 20 robots. How can we do this then? With the means we have available. So education value and easiest implementation was the actual programming task, how to structure your own AI network. So, salute to Mr. Jan LeCun. He really created an excellent exercise, which turned out to be extremely helpful, even when you program robots, not just like video cameras. So, the course had then, of course, the two obvious bottlenecks. We have only one AI model with this complex vision software and only one robot, but we have, of course, far more than 8 students who can join the course. So, how can we expand this to offer more seats on the table? So, we'd like to sort of make our own model for this. And the question then, of course, where do we get an AI model powerful enough to solve this recognition task? And there are 2 ways. Number one, we use this open source model by Autolipted, which is highly developed. How can we adapt it such that it's not only a screening toy, but also interface with robots? They do make advertisements that they offer the entire package ready-made, but then it's not for free anymore. Then you have to pay a rather hefty license fee in order to make that work. So we know it works, but they don't tell us. So how to solve that problem? But we are quite positive. We know that it works, so we just must find a way which works for us. Alternative path, we use our experience with the PyTorch environment to program our own AI networks, which can solve this recognition tasks. Well, so we modify the entire endless database and ask ourselves, okay, how much effort would it be to program a software or code segment powerful enough to create an AI network which can solve this task in sort of very simple and steady environment, which of course it will not be as powerful as Complex Vision, but it will be $10,000 cheaper. Interfacing an AI model is one of the core questions about if you want to AI enhance an industrial robot. So we have to somehow have a program around the entire AI model which handles the interfaces. So what I mean here is that the robot program is sort of in a wait state once it has captured the triggered the capture of the image, and then the secondary computer has to control the data flow to the AI model and then out of the AI model. Complex Vision, nicely enough, came with a C# interface. So after a couple of 100 lines of code, you can make this work. How should we proceed? Now, our idea was, that's nice. We simply replace the AI with YOLO, and we replace Complex Vision by Python code, algorithmic programming, and then it should sort of work. And it can't be so difficult to send a couple of data points into the memory of a robot, right? However, our attempts to use YOLO as a module sort of failed. Not because it wasn't working. It did work, but the problem was the AI models of YOLO are sort of prefabricated. They're extremely intricate, complex, and very powerful. But where should I then put my typical sabotage in? Yeah? So it's very difficult then to sort of sabotage an AI model which is that big and then not get lost in thousands of lines of code segments. So I thought, okay, that's not what I'm looking for. I need some sort of education approach, which I have more control over. So that left us with path B, try to produce our own AI model, which is small enough. There, I have everything under control, and I can sort of nicely sabotage my little template. So the task of this AI model is actually quite simple. Which balls of which color are to be found where? Please give me a list of colors in position. But these are actually 2 questions. Which color is where? So these are 2 questions. The endless task asks only for the class, which kind of letter do we see? So that's only 1/2 of the question. But the standard way to solve this is to actually use 2 AI networks. One class of AI network, and I can tell you in a moment what class those are, which finds the actual candidate for what it might actually be. And then you need a second AI network, which tells what is this, what the AI, number one, actually believes to see in its image. So this is a type of camera image when the robot has moved the camera on top of the little platform and it sees these steel balls. The first AI will tell us, okay, there is something which looks like a steel ball. Please investigate. Maybe this is something. Then the second AI gets sent a list of possible objects and then sent to the classification. Tell us what this actually is. Now, the first part is called a convolutional neural network. It's a multi-dimensional data structure. You don't have to go to the details. I'm just telling you what to do to get an idea of this. The input essentially is a selection of pixels, which each contains three numbers, red, green, and blue. And it's just the colors you actually see. And convolution creates from this yet another multi-dimensional data structure where your picture, your image here, is a vector which has as many numbers behind it as you choose as a programmer. For example, position, size, diameter, these kind of information you can put there. So you make a multi-dimensional data structure into another multi-dimensional data structure by help of convolution. If you want to Google it, maybe. The second structure is then called the feed-forward neural network. That's what the end is past, and that's, by the way, also how ChatGPT essentially functions, is comprised of. There, the inputs, be it multidimensional or two-dimensional in this case, is converted into a one-dimensional vector, and by virtue of inference, it creates an output vector. So you make a one-dimensional data structure into another one-dimensional data structure, where it contains the probability for this object being member of one of the classes. So that's essentially the two-stage approach. So the first network tells us where do we see anything. The second network tells us what do we actually see there. Now, that's a bit of complex code, but the nice thing about the PyTorch environment, if you look at this code segments, sorry, it looks very technical, but that's what AI programming is all about. You see here, convolution layer 1, 2, 3. These three lines already define a three-layer convolutional neural network with just these handful of parameters. Of course, the library framework in the background is creating some monstrous data structure with everything, but from the point of view of the coder who has to run this task, it's actually very simple. Here, for example, you have this three. That means, okay, you have three numbers of incoming channels, red, green, and blue, 3. There, you have here how many channels are going out. At this point, it shows 16 to encode information. Pooling is then a function which reduces pixels by simply taking 2 times 2 pixels and taking the biggest one. That's it. So that's what this entire thing is about. And these 4 lines of code already create an entire 3-layer convolutional neural network. So it's as easy as it gets for the students. They must know how this thing has to be structured. In order to train this entire thing, we have to produce quite a number of more parameters, how the training functions, which functions are used. These parameters are then called hyperparameters. So it's called parameters and hyperparameters. This is the task for the students to find a solution for. Now, we chose then to use the output from the first as input to the second. Of course, you could merge this into one fully enclosed AI network. For these, but it's simply much easier to do it this way because then you can check your success halfway through this entire problem. The question is now how to get this as small as possible. Now, this is actually a slide from my lecture, so don't get confused because it is very confusing. But when you go through this entire sequence of defining and training and going in circles and testing, you sort of get the impression that this is some sort of alchemy. You're sort of pouring toxic things to each other and you stir the pot and hope it doesn't explode. But this is essentially then the reason for my second not so serious slide about AI research. So AI research is really the search of for the philosopher's stone. So in grand sum, it took my one student, Ramona Müller, about 1 year, a bachelor thesis, and 400 working hours to create about 1,600 lines of code, sum total, to actually produce a software which can solve the task. That was a bummer. I didn't expect it would be that difficult, and I was sort of surprised, but I had full confidence in my student that she knows what she's doing, but I didn't expect it would be that long. The last part then is actually quite simple, encoding a signal to a robot. That sounds fancy, but this is nothing more but having here a digital device whose cable go out to the input of the robot controller. There's just some cabling where you have some voltage going in. That's it. Then encoding means the students get a template which can send a 16-bit byte, for example, this number for the 6,797. This will light up on and off the lines, and that's your information. We didn't want to give them some fancy protocol with thousands of bytes. They just should keep it simple. So the challenge then, of course, is the encoding on the Python side must kind of match the decoding on the robot side, and that's what code synchronization is all about. They must cross the line. Now, with all of this AI now available, now we can use our own AI network for expanding our research. So we will tell the students to acquire images, and as you know, labeling images is one of the foundations of modern AI. Data is everything. Then they should reshape the images with some other code segment. They must label the images, and there we use some nice internet page from Oxford. Then they have to modify the Python code and create the code which does the encoding and decoding sequence. Then we create a robot program, and then the enzyme is hopefully complete. But this will probably take for labeling about 2 hours, Python editing 10 hours at least, if they find the hidden sabotage of mine. And then another 2 hours to actually program the robot. Then comes the big dopamine moment. The robot will identify the balls, he will move over, drop the silver one in the right point. Then he will have recognized here the next candidates and continue sorting the robot. That's always then the reward for 1 semester of hard work. So in summary, we reported our experience with our previous announced method about how to teach artificial intelligence machine learning. Our teaching approach so sort of focus on this MNIST problem because that really worked best. In order to expand our course, we sort of chose not to use this open source software, but develop our own AI tool with limited functionality, but more full access to control it in order to interface the robot. So maybe this template will become some sort of new task for robot education. I don't know. Mr. Jan could solve this problem for the one-dimensional inference task. We sort of created a template for two-dimensional convolutional neural networks. This is essentially how we will from now on teach machine vision with robots. We also had some sour experience, and most of them, the AI software project turned out to be far too complex to run this in 1 semester course. My hope when we started this was we would end up with maybe some 500 lines of code, and we could give this as an assignment, but that's simply too much. So I have to give them a template which I can sort of sabotage and see how they find their way through this. But making this all from scratch is simply too much work. So I'm not recommending for you unless you have a PhD student or someone available. Maybe it's something for you. I can give you the source code if you like. The robot control engineering, to my disappointment, is now dominated by 90% programming. I mean, I'm a physicist by education. Now I'm sitting in front of a screen most of the time. That's a bit of a bummer, but okay, you have to adapt nowadays. Most astonishingly, our IT faculty had no intention to join in. That was a really big disappointment. I thought they were sort of scared that they have to do something that actually does something. So maybe that was one of the problems. The outlook is we will copy this solution to multiple robots, which are much simpler and therefore also much cheaper. I mean, with an industrial robot, which I showed you, you have a sort of entry fee of 10,000 euros just for the robot. These robots come at some 2,000 euros. So it's still not for free, but at least we can afford now some 10 examples of those. And this is maybe then our next report in next year. So maybe when you come here, I will tell you what experience we make with that. And with that, I thank you for your attention, and I'm open for questions.